So Spreadsheet Lesson number 7 for our Engineering 1 class. In this lesson, what we're going to do is we are going to tackle a classic engineering problem, and that is, it's the container problem. You've got a limited amount of material. You need to construct a container for a liquid. The top of the container will be open, and what you want to do is find the combination of dimensions that give you the most volume you can fit without spending any more on the materials to make it. So if you think about that, one way to think about this is you'll have a uniform thickness of material, like a sheet good. Like, imagine you've got a sheet of steel, for instance, and you'll be able to cut out different shapes from that, and the total amount of area you use to craft your container will be limited. In this case, we're going to design an open-top container with a surface area confined to 18 squared units, which is actually 324. So 324 units. We'll make that a parameter in our spreadsheet so that we'll be able to change it if you want to say, oh, you think you got more material to make your container out of. And what you want to do is you want to maximize the volume that container can hold. This is actually a multiple part lesson. We're first going to consider a cylindrical container like this, and then later we'll consider basically an ice cream cone. We'll flip this thing over and not use the circle on the bottom of it. So that's what we're going to be doing. It's like a drinking glass. It's got straight sides, and we want to find the values of radius and height that will give the maximum volume as long as the material needed to make it is limited to 18 squared units of space. So the basic, what are the dimensions of R and H, and what is the volume? Now, one thing about this, I found this on the internet, and this is great. It gives us the equation for the volume, pi r squared h, makes perfect sense. And it gives us the equation for the surface area, but this is actually not the equation we want to use, and here's why. We want an open top, so we do not need this part of the equation here. So what I'm going to do here briefly is I'm going to go into, I want to use my stylus here to give you some of this lesson. So I'm going to go into Microsoft Paint, and I'm going to briefly open the image that I just showed you in that assignment right here. And we're going to make some calculations and some changes here. So here's the approach we're going to use. On the spreadsheet, and let's go to the spreadsheet briefly. Where's the spreadsheet here? First thing we need to do in the spreadsheet is I want to add a new sheet. I want to give that sheet the name, and we'll just call it cylinder, Cylinder, cylinder. So there's where we're going to solve this problem. We have one parameter that we cannot change, and that's the area, the surface area that we're given. And that's going to be equal to 18 squared units. So that's kind of a constant we'll deal with. We will go ahead and make it red. Okay? And here's the approach we're going to do. We're actually going to make a guess at a radius. Let's say we do a guess of 1. Okay? And we're going to say if the radius was 1 of this cylinder and the area is 324, then that means there's a certain height that would be associated with that guess. And we can calculate that from the modified version of this equation right here that we're going to be using. And so we'll be able to find the height. And once we know the height and the radius that go together, then we can find the associated volume that produces. So we're going to start with the area and the radius and try to calculate the associated height. And then from that radius and height, we can use this equation to find out what volume it's going to have. Now, this first example is going to have a very, very small base. It's going to be like a tall, thin tube because the radius is only 1 here. Later, we'll go to larger and larger radii. In fact, the smart way to do this is to do multiple guesses of radius at the same time. So what we might want to do is try these guesses in various steps. So, for instance, if we make the radius step 1, our first guess will be for a radius of 1. Our second guess will be that radius plus whatever a step value. Now, we've got to put dollar signs on this so that doesn't change. And what it'll allow us to do is we can let's make, say, like 10 guesses at once. Okay? And then if later we decide, well, maybe we want to look at a little closer, we can go by half as many, or we can restart our numbering at, say, 4. So this allows us to make a bunch of guesses at once, compare their volumes, look for what's best, and we can change our starting point at any time by changing this value here. So let's say that that's a parameter, and we can change our step value, how big it is, how big a jump we make between each of our guesses. So that's the idea. It's sort of guess and check. We're just going to make a bunch of guesses at once, 10 guesses at once, and then we'll zoom in on whatever values give us the best of the volumes produced there. So with that in place, what we're going to do next, and let's change this back to a 1 real quick. So we're going to make the first 10 guesses, radii 1 through 10, and we'll find the associated height. So to do that, we need to do some math. Now, the first thing we have to realize is that in our problem that we are approaching, we are not going to use this area here. That's not going to be part of it because we want an open-topped container. So this 2 disappears in that equation. Also, I don't like using SA. I'll just use A for that. So our actual area equation will be pi r squared. That's going to be this area down here, plus 2 pi r h. Let's talk about where that comes from for a minute. If you think about if I were to cut the can this way and then peel it open, I would get this rectangular result, whose length across the bottom is the circumference of this bottom circle, which is 2 pi r, and the height would be h. So 2 pi r h is this area here, and pi r squared is this area here. So this is the total area needed to enclose this. Now, what we want is to be able to, if we look at our spreadsheet, we want to be able to guess at a radius, have it calculate the associated height, knowing the area is limited to 324. So in other words, we want an equation for h as a function of a and r. So let's just do some algebra here to get to that. We want h by itself. So the first thing we'll do is we'll subtract pi r squared from both sides. So we'll get a minus pi r squared is equal to 2 pi r h. The next thing we'll do is we'll divide both sides by 2 pi r, and I'll actually move the h to the other side. So h is going to be equal to this guy, a minus pi r squared. I'm going to put parentheses around that, divided by this much of this side. We're dividing by 2 pi r. I'm going to put parentheses around that as well for a reason that will become apparent shortly. So that is the h as a function of a and r. That's what we're really after here. What I'm going to do now is a little trick here. I'm actually going to cut this out of this guy here, Control C, that copied it, and I'm going to come over here, I'm going to right click, and paste that in. It's going to come in really huge. I got to make it smaller, but I want to be able to see that equation while I'm working. This is one nice thing about these spreadsheets nowadays. You can paste stuff in from elsewhere if you just want to have a look at it. So that's going to be useful to us as we write this equation to have it handy here. So height is a function of area and radius. So if we have an area of 324 and a radius of 1, then the height will be equal to, let's do our numerator first, the area, which is that cell, minus pi. Now, to put in pi in Excel, you don't type 3.141592. You don't type all of that, and you don't actually type in the symbol pi. The way that these spreadsheets understand pi is you type pi and an open parentheses and a closed parentheses. Now, the open and closed parentheses have to be there, and they have to have nothing inside of them for this to work correctly. But now what we have is area minus pi. Then to multiply, use the asterisk. So this is area minus pi times r. and then we use an up arrow 2 for square. So that is the numerator you see over here, a minus pi r squared h. It's a, which is in cell A2, minus pi times r, which is in C4, squared. We want to divide that, and I'm going to put parentheses around my denominator. Now, the reason I do this is that it makes sure that it doesn't divide it by 2 and then multiply it by pi and r. You really need these parentheses in the denominator to ensure that the equation of the denominator is completed before you do the division. So this will be 2 times pi again, pi, open, close, times r again, r there, close those parentheses. So this will calculate the height that of a cylinder with an open top that has a radius of 1 and a full area of material used to create it of 324. I hit that and I get 51. I am not going to take the autofill for reasons I'll show you in a minute. So I get 51. So this is interesting. It's only 1 inch in radius, but it's 51 inches tall if we're working in inches here. If we're working in square centimeters, then just substitute centimeters for it. Pretty fascinating. Now, of course, that's our first guess. So it's 1 inch in radius and 51 inches tall. If we drag this down, you're going to find that it doesn't make any sense. And the reason it's not making any sense is dollar signs. As it turns out, as I drag this down, I do want to try a different R every time, but I want my area to always remain the same. So I'm going to hit the function F4 in there, and that gives me an equation I can drag down. Oops, didn't quite do that properly. There we go, drag that down like that. So this gets us the height associated with the different radius. And this makes perfect sense. As the bottom of this cylinder gets bigger and bigger around, the height gets shorter and shorter. So this first one, tall, thin, it's like a 2-inch diameter pipe that's 51 inches tall. Here we've got something that's only, it's 10 inches in diameter, 5 inches in radius, and about 8 inches tall. And one that's 10 inches in diameter has almost no height at all. In fact, you will see that if you drag this down one more, we get a negative value here. Now, logically, what that means is that if the radius gets big enough over here in this equation, this part becomes larger than that. In other words, the base uses more area than available to make the thing out of. So you'd have to have negative height somehow to get this to work out. So this is basically saying we pass the logical limits of the equation. So we won't go out to 11 there. This is 13 minutes in, and it's enough for this first video. So I'm going to stop here. We still have a lot to do. We got to calculate the volume. We got to find the maximum value. We got to play around with this stuff here before we actually find out the ideal radius and height for maximizing the volume. But for now, we'll pause it here, and we'll move on to the next lesson.